Okay, so welcome everyone to NPTEL NOC24 EE-143 tutorial. This is the week 1 live interactive session, and yeah, the course is Semiconductor Devices and Circuits. The course instructor is Professor Sanjeev Sambandhan from ISC Bangalore, and yeah, this would be the schedule for my sessions. It would be from 3 p.m. to 5 p.m. All right, let me quickly go through the guidelines. If you have any query, you can either ask in the chat window or you can just raise your hand. And also please make sure that your microphones are muted, especially when I am talking and when you don't intend to speak. If you have a query, raise your hand and then you can unmute and go ahead. Okay. And let's try to make this session an interactive one. And for that, I would appreciate your cooperation. Also keep pen and paper handy so that because we would be solving some numericals as well, so they would be handy. The session recording link and the lecture notes, they will be shared by the NPTEL course team in the due time. Okay, so coming to the prerequisites. The prerequisites for this live interactive session include the following topics that were taught in the last week's lectures. Okay, the excursion in quantum mechanics, which covered the concept of wave particle, the Schrodinger equation, the particle in a box, the finite potential barrier, and the harmonic oscillator. Okay, and I hope that you all have already attempted the assignment 1 before coming to this session. So let's quickly recap what we learned in the last week's lecture, and then we can go ahead and solve some problems. Okay, so coming to the contents, we learned about de Broglie's hypothesis, right? The wave particle duality. Can anyone among you unmute and go ahead and state that hypothesis? What did we learn there? You can either type that in the chat window or just go ahead and speak. Would anyone wish to attempt it? Okay, you can type that in chat anytime. Okay, so de Broglie's hypothesis, what de Broglie stated in that was the electrons and the other material particles, they possess the wave-like properties. In the same way, just as the radiation has particle-like properties. Like we have experiments in which light shows wave-like behavior, and we do have experiments in which light shows particle-like behavior, right? The interference and the diffractions are the ones which can be explained by the wave nature of the light, which is, and the particle nature of the light can be, I mean, to explain the photoelectric effect, we can take help of this particle nature of the light, right? Now, what de Broglie stated was that electrons and other materials, they also possess the wave-like properties. Okay, and there was the de Broglie relation, right? That used to give us the wavelength in terms of the momentum. Would anyone like to type that in the chat or unmute it? Okay. So the de Broglie's relation was lambda is h by p, right? Where lambda is the wavelength and p is the momentum. So, and then we saw an example, right? The professor showed us an example in which realistic values of the velocity uh, were taken for the electron and the tennis ball, right? And then we numerically estimated the value of the wavelength. For suppose an electron travels at a velocity of 10 to the power 5 meter per second, we saw that its wavelength is roughly of the order of 7 nanometer, right? While on the other hand, the particle, we took the mass of the particle around 0.06 kg, a realistic estimate for a tennis ball, and the traveling velocity, we took it as 50 meter per second, which is again a realistic value. And we saw that the wavelength is 9 into 10 to the power minus 32 meter. You can just see the difference in the order, right? For electron, it was 7.2 nanometer, and for the tennis ball, it's around 9 into 10 to the power minus 32 meter. So that is the reason we don't, I mean, witness the wave-like behavior for a tennis ball. Okay, so I guess, yeah, then we read about Heisenberg's uncertainty principle, right? That basically puts a lower limit on the product of the uncertainties, right? Uh, they can be any two observable quantities. I mean, we'll see later as well. Delta P delta X is greater or equal to h bar by 2. So the product of the uncertainty in momentum and the uncertainty in position, the lower limit is h bar by 2, right? In the similar way, the energy and time also follow this relation, right? So delta E times this delta T is greater or equal to this limit. Okay. Then we saw Schrodinger equation, right? Schrodinger equation, which is given by this. You can see that there are space derivatives and time derivatives, and this is actually I mean, arguably this is one of the most important equations in the whole quantum mechanics, right? And we also learned about the wave function, right? The wave function psi is solution of this equation, and it is a mathematical description. And we also learned that it follows certain properties, right? The wave function psi has to be continuous, right? And its derivative also has to be continuous, right? It should not blow up, and all the other properties that we saw. I'm sure you all must have gone through them. Then we, I mean, came to particle in a 1D box problem, where, which is, I mean, the infinite barrier potential well problems. So what were the key observations there? We saw that the energies are discretized, right? They are quantized. It cannot take any value, take certain number of values, right? So let me write it. For this, we saw that E is n square h bar square pi square by 2m a square, where this n can take values 1, 2, so on, right? And what is the 0 point energy for this problem? It would be, what is the 0 point energy? First of all, 0 point energy is the lowest energy, I mean, that this, I mean, particle can take in a quantum mechanical system. Okay, and for this one, it would be corresponding to this n equal to 1, right? Similarly, then we saw finite potential barrier problem, right? What were the key observations there? Would anyone point those out or write them in chat? I can wait 1 or 2 minutes. Can you guys unmute yourself? I mean, try unmuting yourself and just see if you can unmute yourself. I hope you guys can unmute. Anyone? If you cannot unmute yourself, just write no, we can't, so that I could look into it. There. Okay. Okay, someone is typing. Okay. There is a probability of finding the particle outside the box in a finite potential well. Yeah, that was one of the key observations, that unlike a classical systems, and also one more thing, the case is E less than V naught, right? Where V naught is that finite potential, and we are talking about the energies that are less than that value, right? Classically, there is no way, I mean, the particle can escape it, right? Unless it would have energy E that is greater than V naught, right? But as long as this is the case, the particle, there was zero probability of finding the particle outside the box. However, in quantum mechanics, there is a finite probability of finding the particle outside the box. Okay, so that is one key observations. Would somebody like to try what was the other key observation? I won't be dwelling into the derivation since they already have been taught by the professor. I'm just trying to point out the key observations and just brush up them. What is the another key observation that we saw in finite potential barrier? Okay, I guess let me write it. So the other thing that we saw in this was the probability of finding the particle outside the well, it decays exponentially, right? See, if this is your well, this is V naught, the probability decays exponentially, right? I mean, wait, I'll use some pens, right? This is V naught. So by this blue color, I will be showing the plot of probability. So the probability, I mean, wave function, we know how psi x. By the way, what is the expression of wave function uh, in infinite potential well, the particle in 1D box? Please write that in chat. Meanwhile, I'll explain finite potential barrier, the observation, one of the other key observations apart from the one that Shailendra typed. So the probability decays exponentially, right? This P is directly proportional to e to the power minus kx, right? Where this constant k is proportional to the square root of e minus v naught, right? Yeah, we are talking about this case. Okay, the question is still open. You can write in the chat. What was the expression of the wave function? What was the form of the wave function that we got when we solved particle in 1D box problem, right? I mean, not necessary you would point out the exact function, but at least the form that that function it take. Please write that in the chat. I'll proceed meanwhile. So yeah, again, in this finite potential barrier, the 0 point energy was corresponding to n equal to 1, right? Then we had the harmonic oscillator, right? The last topic. In that, what was the key observation in that, by the way? Yeah. So I guess I should write in the chat what was the wave function form we got in a particle in 1D box within the box. This is one of the questions. The other one is, what is the key difference between classical harmonic oscillator and quantum mechanical harmonic oscillator? You can answer that in the chat, okay? I'll just wait for 1 minute in case anyone answers it, and then I'll answer it myself. All right. So the wave function form that we got in particle, sorry for the typo, it's particle in 1D box. Within the box was psi of x is a sine of kx, right? And regarding the other question, I guess someone is typing, I'll again wait. A sine of pi x. I guess you mean a sine of kx, right? For this one, right? Yeah, okay. So this one is done. What about the other one? The second question. What is the key difference between the classical harmonic oscillator and the quantum mechanical oscillator? Okay, I would give you a hint. The hint is the 0 point energy is different in both. What is the 0 point energy? 0 point energy is the lowest allowed energy state, right? Classically, what is the lowest energy that this oscillator can take? You can think of it as a spring that is vibrating, right? Classically, the lowest value it can take is 0, right? Corresponding to 0 momentum and 0 kinetic energy, right? However, we saw for quantum mechanical oscillator, the 0 point energy was non-zero, right? Let me write the expression. So what we saw was classically, I would denote 0 point energy by E0, okay? Classically, E0 was 0. However, quantum mechanically, this E0 came about to be, it was h bar omega by 2, right? H bar omega by 2. In fact, the professor solved it for the ground state, right? In the example that the professor, considered for the harmonic oscillator, he considered ground state there, right? He mentioned that as well. So ground state is nothing but the 0 point energy, right? So that is the lowest allowed energy state. So that is non-zero. In general, what is En? In general, En is n plus half h bar omega. Okay, and then n can take values 0, 1, 2, and so on, right? N can take value 0, 1, 2, so on. So that finishes up this brief recap. If anyone has any questions regarding this brief revision that we just finished, he or she can go ahead. You can either unmute yourself or type in whatever you like. Anyone? Okay. I guess no one has any doubt. So we will now start with the questions then. Please try to be more interactive. This session is supposed to be live interactive one so that you could benefit. So the first question is the wave function of the particle. It must be normalizable because option A, the particle's momentum must be conserved. Option B, the particle cannot exist at two places at the same time. Option C, the particle must exist somewhere in the space. Option D, the particle's charge must be conserved. Give it a thought and type it in chat. This is an easy one, and I expect many of you to solve it and answer it in chat or by unmuting yourself. And also at any point of time, if you think I'm not audible, you can just tell me and I'll check it. So please type the answer. Is it A, B, C, or D? Okay. C, the particle must exist somewhere in space. I'll wait a little while. Okay, we got two C's. Anyone else who would like to attempt this? Three C's. Okay, four C's. I guess I got answers. So yeah, that is the correct answer. The reason being the wave function, it must be normalizable because it represents the probability of amplitude of finding a particle in a given state, right? In fact, what exactly is, I mean, express the probability amplitude of finding the particle in a given state in terms of wave function. What do we do to the wave function? I mean, wave function as such does not give us probability, right? We do something to the wave function, right? I'm asking about that. Square integral is 1 to minus 1. Square integral. Okay, if this was in response to my this query, no, I mean, see, what I'm saying is Suppose you have psi of x, right? This was your psi of x. But what about probability finding the particle at a given point x? We do something to the wave function psi of x, right? What is that something? Remember? Modulus square, right? This would give the probability density function. Fine. So it must be the wave function. Coming back to our this question, the wave function of the particle, it must be normalizable because it represents the probability amplitude of finding the particle in a given state, right? And what is the total probability of finding the particle anywhere in the space? What is the total probability equal to? That is equal to 1, right? So that is uh, I mean, that inherently requires the wave function to be normalized, basically, right? So this means that the integral of the square of the absolute value of the wave function over all space, it must be equal to 1, right? I mean this thing, minus infinity to plus infinity, this should be equal to 1, right? You can turn off your video. All right. Okay. So is this clear? I hope this question is clear. I'll move ahead. This was easy one. So the next one is if psi1 xt and psi2 of x comma t, wave functions that are functions of position and time, if these are two physically realizable states, you need to show that any linear combination of the two states is also physically realizable. Okay, I guess I'll start this directly. So I have mixed the questions. Some of them are, derivation based, and most of them are multiple choice questions. Okay, this one is derivation based, so let's go through this. So psi1 xt, wait, and psi2 x comma t, they are two physically realizable states, right? So what does that mean? Minus infinity to infinity a square psi1 x comma t whole square dx, that is, less than infinity, right? That does not blow up, in other words. Also minus infinity to infinity b square psi2 x comma t dx less than infinity, right? Now what about the linear combination of the two? For the linear combination, we can write it in this way, right? We need to ultimately show that the integral for the linear combination is also less than infinity, right? That would, in other words, prove that the linear combination is addition of both the terms. Yeah, but in general, there would be constants as well, right? See, if A and B are two vectors, the linear combination can be, let me take, no, wait, I'll take X and Y as vectors, right? It's better to keep constants for A and B. So then A times X plus B times Y is the linear combination of the two, right? In general. Yeah, the addition of both the terms is a specific case. Okay, I hope it is clear. So let's write the linear combination of the two. Also, I can write, yeah, let's write this. This would be A times psi1 x comma t plus B times psi2 x comma t, sorry, I mean modulus, right? Square dx. We need to show that this is less than infinity, right? We have not been given that yet though, but we have been given these two. Okay, then minus infinity to plus infinity. I can write this mod z square as zz conjugate, right? Since this in general would be a complex number, right? So let me write that. Psi1 xt plus b psi2 xt whole square. I mean conjugate, right? This conjugate and then plus b psi2 x comma t dx, right? Then we can, I mean, after some manipulation, we can reduce this to following terms. Let me add a page though. Add another page. Mm, fine. This is the page. So you can show that if this is suppose I, this I would be equal to, I mean, do this at your own end, okay? This would be minus infinity to infinity a square psi 1 x comma t square dx plus minus infinity to infinity ab psi 1 star x comma t x2, I mean psi 2 x comma t dx plus minus infinity to infinity ba psi 2 star x comma t psi 1 x comma t plus minus infinity to plus infinity b square psi 2 x comma t whole square dx. Okay, what I did was, firstly it was conjugate of this, right? So I would do is I would apply conjugate to psi 1 and psi 2 individually, and then after, I mean, after product multiplications and manipulations, you would obtain this. Okay, try this at your own end. That would save us some time. Then what would we do? Then we would use this Cauchy-Schwarz inequality. Wait, Schwarz inequality that states that if x1, I mean psi1 of xt and psi2 of xt, they are square integrable. If this is the given case, then the following holds good, right? Then their inner product is guaranteed to exist. Okay. So modulus of A to B psi 1 star of x psi 2 of x dx, it is less or equal to the square root of, right, the inner product is guaranteed to exist. So this would be A to B psi 1 of x whole square dx integral A to B psi 2 of x, modulus of this square dx. Just a second. All right. So yeah, see if psi 1 of xt and psi 2 of x of t, they are square integrable, then their inner product is guaranteed to exist, right? And then I used this Cauchy-Schwarz inequality. Okay, so it basically sets an upper bound on the inner product of the two vectors, right? In terms of product of the vector norms. Okay, these are the vector norms. So this that I have used here is the Cauchy-Schwarz inequality. Okay, let's move ahead. Now, what do we know? We know that this minus infinity plus infinity a square psi 1 xt this whole square dx, this is less than infinity. Why? Okay, similarly minus infinity to plus infinity b square psi 2 x comma t, that is less than infinity, right? And the minus infinity, this was also there, right? This one. So minus infinity to plus infinity psi 1 star x comma t psi 2 x comma t dx would be less than infinity, and minus infinity to plus infinity, uh, the conjugate, right? The psi 2 x comma t star psi 1 x comma t dx would be less than infinity, right? So if that is the case, then this I would be less than infinity, right? And this I was a linear combination of these two states, right? So this implies that I would be less than infinity, thus the linear combination is also physically realizable. Okay, we are done with the second one. So now the third one. Which of the following is not a valid quantum mechanical wave function? Please show the question once. I mean, okay. Do you mean this one? 540. Uh, could you again write, did you mean, should I show this question too? Okay, I guess you were talking about this question third. Yeah. Okay. D. Fine. Anyone else? We got 2 votes for D. 3. Anyone else who would like to attempt this? And those of you who have written D may go ahead and, I mean, either write in chat the explanation as to why do they think D is the right answer, or they can unmute and just tell it. Okay. Meanwhile, others, you can attempt. Is it A, B, C, or D? Okay, so Shailendra is writing that the wave function should be continuous, and this is not continuous. Yes, that is the correct answer. In fact, I got two same explanations for this. The other one, the other guy has also written it that it is not continuous. So yeah, the psi obeys certain properties, and one among them is that the psi has to be continuous, right? So psi should be continuous, right? So this one is the right one. Okay. Regarding the chat, somebody had written, please show the question once. It was with reference to question 3, right? Or was it with reference to question 2? Could you clarify it once? Okay, 3. Then it's fine. Right? We are done with the third. Does anyone have doubt? Right? It is discontinuous, right? At this x equal to 0. Okay, someone is typing. I guess I would wait. Okay, never mind. So with that, we'll move to the next question. Let psi be any wave function. This one is relatively short. I mean, this should not take much time. Oh no, this is lengthier than the previous problem. And after this question number 4, the rest of the questions are multiple choice questions. That won't take too much time. Or let's do one thing. We'll keep the question number 4 towards the end. Meanwhile, let's try to attempt shorter problems first. Okay. What about this? The value of the commutator. xp. In fact, this is a standard result that you guys should be knowing. What is the value of this commutator xp? Iota h. Okay, I would take this as iota h bar. If that is the case, then this is the correct answer. And also, what is the significance of this commutator operator? Firstly, commutator operator AB would be given by, AB minus BA, right? It's as if, suppose I'm operating this operator on psi, and this is how it would look. So uh, B would operate on psi first, then A would operate on the result. We need to subtract that from the quantity in which A operates on psi and B is operated on that result. Okay, someone is saying that it is identity operator. What do you exactly mean by the identity operator? And how would you define an identity operator? Please explain. Okay. See, the significance of this commutator operator is that it tells us if we can measure two observables at the same time, right? So whether or not we should go ahead and use Heisenberg's uncertainty principle or not, right? This x and p, if you remember, we had written this delta x delta p that is greater or equal to h bar by 2, right? This we wrote, the reason being the x and p, right? Their commutator is non-zero. Had it been zero, then we would have been able to measure both the observables at the same time. Is that clear? Fine. So yeah, this is how we define commutator operator. Although it has already been answered in the chat that this is iota h bar, but I'll still go ahead and show how that comes about since only one of you answered it. So x p psi x, right? This is what we need to solve. This would be equal to x. What is the operator for the momentum? Anyone? The operator for the momentum? P. Yeah, that is, I guess you confuse it with the symbol. See, if x is the operator, we use x, right? What about P? What do we write? H bar by iota, dou by dou x, right? This is the operator that we use for P, momentum, right? This was taught in the lectures. You can revise it if needed. So now coming to back to this question, see, x operator, P operator on psi means P operator, x operator acting on psi of x, right? We need to compute this difference. Operator x is nothing but position x. Regarding P, this would be h bar by iota, dou by dou x of psi x, right? Minus p. P is h bar by iota dou by dou x, right? What is inside the bracket? Operator x, psi of x. But what is operator x? That is x, right? And psi of x. So inside this bracket, it's product, right? X times psi of x. Now, yeah, this would be, let's write this as such, dou by dou x, psi of x. What about the second term? We can use product rule, right? H bar by iota. This would be, let's keep psi of x as such and differentiate x on both sides. That would be, I guess I'll show the step as well. Psi of x dou x by dou x plus x dou psi of x by dx. Is that clear? Yeah. So this would be x h bar by iota dou minus h bar by iota psi of x. Well, this dou x by dou x is 1, right? And then I have minus, right? H bar by iota x dou psi of x by dx, right? Now notice that this and this term should go, and what was on the left hand side? It was operator xp acting upon psi of x, right? So if this and this will go, we'll be left with this part, right? That would mean that this xp commutator of x comma p, that would be equal to, now what is 1 over iota? What is 1 by iota? That is minus iota, right? So minus and minus is plus, so it would be h bar iota, right? See, it's minus iota h bar psi x. I can write that as h bar iota psi of x. Notice, I mean, I'm not showing now psi of x on the both sides because I was interested in finding the value of this operator, right? The operator does act upon the psi of x, but we were interested in this quantity, and we obtained it. So that is what was answered in the chat as well. So now moving on to the sixth question. Consider the following 5 plots as a case for a particle in an infinite potential well of length L in graphs A and D, this and this one, A and D. You need to, list the properties that are violated. Please go ahead and write them in the chat. Is the question clear? Okay, someone is saying, in fact, it's okay. We got 2 Ds. Anyone else who would like to attempt this? In A and D, is there any property that is violated? Because if no property is violated, then what these guys wrote in the chat, D, should be the right answer. So it turns out that is indeed the case, because see, for this and this one, the derivative as well as the psi as well as its derivative, they both are continuous, right? I mean, this is also wrong. Why? Because it is normalizable as well, right? And yeah, none of the properties are violated. So the answer is D. Fine. Does this need any more explanation? Okay, I'll assume no. Now question number 7. In graphs B and E, the properties that are violated are, which are the properties that are violated? These two. D. So you are saying derivative is not continuous. Anyone else who would like to attempt it? Okay. So I only got one response this time, and that is D. So the derivative is not continuous. See, for this one, although this psi is continuous, but if you take the derivative of this, what would be its derivative? Its derivative would be something like this, right? So there would be discontinuity here. No, wait, its derivative would be something here, right? It is a positive slope here and a negative slope here. So there would be discontinuity at this x equal to 0. So derivative is not continuous for B. Similarly, derivative is not continuous for psi of x as well in E. Now what about, I'm moving ahead. Is graph C an acceptable plot for psi? No. Okay. Anyone else who would like to attempt this? Okay. I only got one response. So why is this not acceptable? Let me ask you then, to the student who replied no. Derivative is not continuous. Yeah, correct. So this is not acceptable. Let's move forward. Right. Are others fine? Right. It's pretty straightforward, right? The derivative won't be continuous, right? Again, same issue. For this part, the slope is positive, negative slope, discontinuity. By this red line, I'm showing what its derivative would look like, right? So this one is done. What about this? If the ratio of the maximum and minimum intensities in an interference pattern is 49:1, then the ratio of the amplitudes of the two interfering waves will be. Okay, let's do this step by step. What is the intensity of the wave proportional to? I mean, is there any relation between the intensity and the amplitude of the wave? I'm asking, say the intensity is I, right? You know the amplitude of the wave, that is A. Intensity is proportional to some function of A, right? What is this function? It is A square, correct. So this would be right. I guess I would write, see, intensity would be proportional to A square, right? And one more thing, when will the maximum intensity be formed? Hint, it is, I mean, related to their phases. Should the phases be in phase or out of phase? At the same phase, you mean in phase, right? Correct. And when will the intensity minima occur? Yeah, when they are out of phase. So now the second question, when the amplitudes are in phase, right? And suppose the two amplitudes of the waves are A1 and A2. What will happen to the amplitudes when they are in phase? See, when you have this, remember in general it was A1 square plus A2 square plus uh, wait, was, yeah, 2A1 A2 cos of, say, suppose this phi, right? You saw this relation, right? So when it's in phase, right, what will happen then? I mean, I'm trying to compute A. What would be this A when this phi is 0? This everybody should answer. This is straightforward, right? When phi is 0, this would be, no, it won't be A1 square plus A2 square. Think again. See, cos of 0 is 0. Sorry, cos of 0 is 1, right? So you cannot cancel that. A1 plus A2 square. Yes. Yeah. The second one is also the same thing, right? A1 square plus A2 square plus 2A1 A2 is A1 plus A2 square, right? So I'll write this A. Let me write this as max. Okay. This would be a1 plus a2 square. Okay, yeah, a1 plus a2 square. Now, what about this minima? When this phi is out of phase, by out of phase, when it's out of phase, phi is 180, right? What is cos of 180? If possible, unmute yourself. That would save us time. Yeah, cos 180 is minus 1. Okay. Somebody in fact answered it. A1 square plus a2 square minus 2a1 a2. And you can reduce this to this a1 square plus a2 square minus 2a1 a2 reduces to, reduce it to something similar like this. A1 minus a2 whole square, right? A1 minus a2 whole square. Fine. But we were not asked about a max and a min. In the question, we were asked about the quantity that was given was the ratio of the maximum and minimum intensities of the interference pattern, right? So what is given is I max to I min. Okay, somebody computed the answer as B. That is the correct answer. Good, good, good. 1.33. Fine. I guess I'll still do it for the sake of others. I max by I min is 49 by 1, right? And but this I max is proportional to A max, right? Which is nothing but A1 plus A2 square, right? Similarly, this I min is proportional to A1 minus A2 square, right? Then if you take the ratio of these two quantities, you'll get this, right? So this is 49 by 1. So if I take this, then the following holds good, right? This A1 plus A2 by A1 minus A2, this would be equal to 7 by 1, right? And if you'll uh, go ahead with the manipulations, you'll get 8 times A2 is 6 times A1, right? So A1 by A2, that would be equal to 8 over 6, right? See, we were asked to compute the ratio of the amplitudes, right? That's why I'm doing A1 by A2 would be from this equation. 8 by 6, which is nothing but 1.33. That the two students wrote in the chat. Fine. Does anyone have any doubt? Okay. Uh, can anyone among you unmute yourself? I just wanted to check if you can unmute or not. Just unmute yourself and say, yes, I was able to unmute. That's it. No, sir. My mic is not working. Okay, okay, okay.
Yes, sir.
Okay, someone was able to unmute, I guess, because I heard sound.
Yes, sir. Sir, can you
Yeah,
hear?
yeah, 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 yeah. Thank you. So maybe you can check the student who is writing that mic is not working. So I guess the problem is not of the platform, right? So then it's fine. So now moving on to the next question. A small 0.4 kg cart, it is moving back and forth along an air track between the two bumpers that is located 2 meters apart. So you can assume that there is no friction present. Collisions with the bumpers, they are perfectly elastic, so that between the bumpers the cart maintains a constant speed of 0.5 meters per second. You can treat the cart as quantum mechanical particle, and then you need to uh, find, or I mean computer find an estimate of the value of the principal quantum number that it should correspond to. I mean that corresponds to its classical energy. How should we proceed this one? Even the approach would suffice me if you don't say the answer. I'm not audible. Am I audible? Hello? Is it audible now? Okay, I am audible. I guess maybe then that student would be having issue at her own end. Fine. So where was I? The energy of the cart, right? Firstly, the friction is not present, right? So you can assume that the energy of the cart is completely kinetic, right? And if it's completely kinetic, then that E, by E I mean the kinetic energy. I guess I should write K for this. The energy would be N square times the E1, right? E1 is the ground state energy, right? So if we need to find N, then that N would be equal to K by E1, right? But what is 6 into 10 to the power? Let me check. Have I written 6? No, 6 is not the correct answer. You can meanwhile keep trying it. I'll also continue at my end. So what is kinetic energy K? See, K is half of mv square, right? So you have been given mass, right? And you know the velocity as well. So you can compute this. Uh, I mean, you can compute this kinetic energy, right? And you can verify it comes out to be 0.05 joule. Okay, just check it once. What about this E1? Let me add another page. What is the E1 that we wrote here? Remember that formula, E is equals to N square H bar square by, wait. 2ml square, right? This was the formula, right? Is it 6.03? No, still that is not the answer that I got. Keep trying again. So what should be E1? E1 is this part, right? This part is E1. So the E1 that you get is pi square times what is h bar square? The value of h bar is 6.636 into 10 to the power minus 34 whole divided by 2 pi whole square, right? Whole divided by 2 into 0.4 into what was this length? 2 meters apart, right? So this is 2 squared, right? If you'll solve this, you will get E1 to be 1.7 into 10 to the power minus 68 joules, right? Now it should be easy, right? You know this, you know this, so you can find out this n, right? So what is the value of n that we get? I'll wait for you guys to answer. This should be simple. Okay, I'll write it myself. This should be k by this would be 1.2 into 10 to the power 33, right? This is what you would get. So why is that we got such a large n, right? This principal quantum number n is way too high, right? Why is its value so high? Remember, this problem was classical, right? It was not quantum mechanical. So what did went wrong is because it is macroscope. Yes, I mean the energy of the classical system, since it is classical systems, a very large this principal quantum number n characterizes the macroscopic systems. So that is the reason why we got this large value of n. So I guess we can move ahead. Attempt this one now. So if the position of an electron in an atom is measured to an accuracy of 0.01 nanometer, then what is the uncertainty in electron velocity? Okay, this is simple Heisenberg's uncertainty rule problem. You should be able to solve it. I'll wait for you guys to solve it. Right? All of you start solving it. See, we are considering, I mean, we are neglecting relativistic effects. So this H, where it is, I mean, this delta P, right? You can write this as M delta V, right? In general, this should be m delta v minus v delta m, but we are neglecting this term, right? Ignore that. Now solve it. Okay, I guess I do have some answers. Into 10 to the power minus 23. Why did you get so small value? What is the unit? Meter. No, this is not the correct one. See, what is the value of this mass of the electron that you took? The mass of the electron is 9.1 into 10 to the power minus 31 kg, right? I think using that you should have got the right answer. See, what I'm trying to say is delta x, our delta x is this 0.01 nanometer, right? Our delta x is 1 nanometer. And see, m is 9.1 into 10 to the power minus 31 kg. And delta v is something that we need to compute. So what you can write is delta v is equals to, we are taking this lower limit, h bar by 2 m delta x. This is what you needed to solve. Six 6.63 into 10 to the power minus 34 joules, right? Sorry, joule second, right? Joule second, yeah, the unit should be joule second, whole divided by 2 into 9.1 into 10 to the power minus 31 into what is delta x? Delta x is 0.01 nanometer. Okay, so that would be 10 to the power minus 11 meter. Okay, someone is saying 5.27. 5.27. No, that is also not the correct answer. Okay, wait, I forgot that 2 pi factor. This is now reduced to a substitution problem, right? Just plug in the values and let me know. Everybody try this out. 5.78. Okay, I'll try this myself now. See, this was 6.63 whole divided by 4 pi into 9.1 into C 10 to the power minus 31. If this goes there, this should be 10 to the power minus 3, right? And then we have the 10 to the power 11 factor from here. Did I miss anything? No. This would be, okay, 5.8. I don't know. I'll solve it once again myself. Meanwhile, you other guys, you also can verify it. Should not be that hard, right? It is 6.63 whole divided by 4. Yeah, the answer that you get is 0.058 into 10 to the power. Yes, whoever said 5.78, 5.8, you guys are right. Just let me sort out the units though. Should be 10 to the power 8, but it is meters per second, right? Then it's 2 to this would be 5.8 into 10 to the power 6 meters per second. We need to report the answer in kilometers per second, right? So this should be 5.8 into 10 to the power 3 kilometer per second, isn't it? Is it? Does everyone agree with this answer? Fine. If everyone agrees, I'll move ahead. Now this is the second last question. Actually the last one, but since we left one question, that's why we are left with two questions. We are yet to do question number 4, right? So try to attempt this one. A particle moving in one dimension, it is in a stationary state whose wave function is given by this one, right? Where this a is real constant. You can use a equal to 3, okay, and find the magnitude of the a so that this wave function is physically acceptable. Okay, how would you approach this one? When is the wave function physically realizable? Right, we are asked that we need to find the magnitude of the a so that this wave function is physically acceptable. I'm asking you, what is the condition on the wave function imposed when it is physically acceptable? It's simple, right? It is minus infinity to infinity integral mod psi of x square dx should be equal to 1, right? That should be equal to 1. So you need to use this one, right? Use this one, minus infinity to infinity psi of x square dx, and this is your, I mean, psi or phi, whatever. In this question, your psi of x is denoted by phi of x, right? So I guess I should change it. Now, can you solve it? First, quickly, what will happen to the limits from for x less than minus 8 0, right? For x, if it's 0 for x less than minus a, then from minus infinity to minus a, this integral would be 0, right? So you can write this. Lower limit would be minus a. What about the upper limit? From a to infinity. Yeah, the upper limit would be a. because integral a to infinity phi of x, that would be 0. So this phi of x square dx should be equal to 1, right? Now put in the value of shit. Just a second. Yeah, minus a to a square of this, right? So it's a square 1 plus cos square pi x by a. Answer is 1 over 3. Correct answer. The answer is 1 over 3. I'll still complete for the sake of others. Yeah. So this square dx, and you can write this as minus a to a square can be plugged out. We are left with 1 plus 2 cos of pi x by a plus cos square pi x by a. Correct me if I make any mistake somewhere. Dx, right? So is this clear what I did? See, cos square y, that is equals to 1 plus cos of 2y whole divided by 2. I've used that one. Let me just check. Wait. Should be minus a to a square. See, if I use this identity, this would be equal to 1 plus 1 is 2, 2 plus uh, cos of 2 pi x by a. No, wait. Why would I use in this step? I already solved it this much, right? I'll use it on this one, right? Because expressing in terms of linear powers would help me to integrate it easily, right? You can do it keeping it this way as well, up to you. Minus a to a phi of x square dx, that is equal to, well, that is equal to a squared, again minus a to a, it is, just verify at your end, it would be 3 by 2, 2 cos of pi x by a plus half of cos of 2 pi x by a dx. Alright, I guess we'll write some part on the thank you slide as well. Well, this minus infinity to infinity, this is equal to 1, right? And then this was carried all the way till down. So I'm writing this as 1. 1 is equals to minus infinity to infinity psi x square dx is equals to a square minus a to a dx I mean a 3 by 2 factor, right? Because for the remaining it would be 0, so I'm only left with this part. This and this goes to 0, right? From minus a to a. So yeah, this would be 3a square, right? Because integral from minus a to a dx is 2a. 2 and 2 cancel out, it's 3a capital A square. And then our this small a is equal to 3, right? So a square should be equal to 1 by 9. This implies a is 1 over 3 or 0.33. Now moving on to the question that we had left. Let's quickly try this one out. I mean, I'll try to finish it, but if we go beyond the time limit, you guys can solve it and let me know if you face any problem in the next session. Okay. Also, one more thing, could you write in chat if you are okay if we use Microsoft Teams for this? Would you prefer Google Meet instead? Okay, so Microsoft Teams does not have any issue. In case if there are some students who would prefer Google Meet, you can let me know. Anyways, you'll have access to slides, so you'll have my email ID as well. You can just email me and let me know, or we can write in the chat here as well. So let me solve it. Can we have your email ID? Yeah, this is my email ID. You'll get access to slides, so you can mail me from there, or maybe you can note it down if you need it earlier than that. Yeah, we were on the question number 4. Let's quickly try to finish this one. See, psi of x comma t is a wave function, right? So firstly, this expectation of position is given by minus infinity to infinity psi star x psi dx, right? What about this d by dt of expectation of position? This would be equal to d by dt of this particular thing, right? Instead of writing it, I'll just copy. We'll save our time, right? This particular quantity. Then you can write this as follows. This would be d by dt. Wait, you can write this as follows. You can write it as minus infinity to plus infinity x d by dt, right? And then you have the reason I took x out of this d by dt is because x does not depend on t, right? It is derivative with respect to t. That's why I took x outside. So it is psi star psi dx. Why did I keep psi inside this d by dt operator? The reason is because psi is a function of position and time both. Okay, so it will have some time dependence. That's why I cannot out of this. So then d by dt of expectation of position, that is equals to minus infinity to plus infinity x psi d psi star by dt plus psi star d psi by dt to be integrated with respect to x, right? Then I'll use Schrodinger equation. What is that? Iota h bar d psi by dt, that is minus h bar square by 2m dou square psi by dou x square plus v psi. This is the Schrodinger equation, right? We all are familiar with this one. So what I'll do is I'll rearrange this. I can express it as follows: d psi by dt, that is equals to h bar iota over 2m dou 2 psi by dou x square. We can just quickly verify this as well. Minus iota h bar v psi. Right, let me mark this one as first. And if I take conjugate of this, what will I obtain? D psi star by dt h bar, I'll have a minus sign, right? Iota would be replaced by minus iota 2m dou 2 psi would be replaced by psi star dou x square. Minus would be replaced by plus psi, right? This would be v psi star. This is your 2, right? Then using 1 and 2, what I can do is I can compute following quantity: psi d psi star by dt plus psi star d psi by dt, right? From 1 and 2 you can obtain this quantity, right? What would be the right hand side? Just verify, you'll get this one. I'm skipping, I guess, 1 or 2 steps here, but you guys can verify them. They are pretty straightforward. Psi star d2 psi by dx square minus psi dou 2 psi star by dou x square. I'll keep this as third. You will verify it. I'll proceed. Then I'll take derivative of this. Dou by dou x of psi star dou psi by dou x minus just a second. Okay, now what about this particular quantity? Dou by dou x. Let me put a check mark. Now dou by dou x psi star d psi by dx minus psi dou psi star by dx. This would be equal to psi star as it is dou 2 psi by dou x square minus psi dou 2 psi star by dou x square. Right, I'll keep this as 4. Again, I skipped one step here, which is left as an exercise for you. Then I'll use third and fourth. I'll get following. d d by dt of expectation of x. Right, remember? We were interested in finding this integral. Now we have this expression for this one, right? So I'll write this as h bar by iota whole divided by 2m integral minus infinity to plus infinity x dou by dou x psi star dou psi by dou x minus psi dou psi star by dou x. Right. Then hold on. Yeah, then I can use integration by parts, and then I'll get this one using integration by parts. You'll get this one h bar iota by 2m x psi star dou psi by dou x minus psi dou psi star by dou x from minus infinity to plus infinity. Alright, and we have this one minus h bar iota over 2m integral minus infinity to plus infinity psi star d psi by dx minus d psi star by dx psi dx, right? Now, with this should be 0. Why? Because psi should tend to 0 when x tends to plus or minus infinity, right? So I'm left with only this part. I'll add another page. It will only take 5 minutes now. So let me write reason psi should tend to 0 when x tends to plus minus infinity. All right, so that gives me this rate of change of expectation of x is equals to minus h bar iota by 2m minus infinity to infinity psi star d psi by dx minus psi d psi star by dx to be integrated with respect to x. This would be minus h bar iota by 2m minus infinity to plus infinity psi star d psi by dx minus psi star minus infinity to plus infinity plus integral minus infinity to plus infinity psi star uh yeah, it's fine, dx, right? This would tend to 0. See, psi has to tend to 0, right, as x tends to plus minus infinity. So our rate of change of expectation of x position is minus h bar iota by 2m minus infinity to plus infinity 2 times psi star dou psi by dou x dx, which gives the final answer as minus infinity. Wait, this 2 would cancel out, right, with this 2. So I'm left with this psi star d psi by dx dx. Okay, we are done with this. Rest of the questions we have already finished. So does anyone have any query? We still have 7 minutes left. If you have any question regarding today's session, you can let me know, or if you have any feedback, you can just type in the chat. You can drop me an email if you have any query. When will the answer of the weekly assignments be given? Okay, it would be given after your evaluation. Right? It won't be before that. When is the deadline though? I guess first week, at the end of the first week of August, right? Should be around that, 7th or 8th August. So Perhaps after that, I guess. See, I'm not sure, but maybe when the second assignment would have been evaluated, you should probably have access to the weekly assignment solutions. Any other doubt, especially regarding today's session, or any problem that we solved today? I guess no. Fine, if you guys have any sort of feedback, feel free to mail me. If no one else has any question, we can probably end the session here. Thank you for attending till the end. Please leave the meeting if you don't have any query.